So first, let us define grids. A grid is a structure on which the loads are applied perpendicular to the plane of the structure. So how is this different from a frame? When we worked with frames, the frames were, let's say if this is the XY plane, the planes or the structure of a frame is in the XY plane, and the loads are also in the XY plane. But when we're talking grid, if the grid is in the XY plane, then the load will be applied in the Z direction, right? So if I want to describe it, if I consider, for example, let's make this here X, Y, and Z. So a grid could go like this. And extend so you see my structure is in the XZ plane. And this structure will be subject to loads that are perpendicular to the plane. So the loads here are acting in the Z directions. So the load in the Z direction or perpendicular to the XZ plane, which is the plane of the structure. So we said here, the grid is a structure in which the loads are applied perpendicular to the plane of the structure. And for frames, the loads are applied in the plane of the structure. So just so that you can compare, you see the difference. Yes.
Loads in the Y direction, right?
Yes, I said Y and I wrote Z, right? Thank you. You are correct. Yeah. Okay. Like frames, the elements of a grid are assumed to be rigidly connected. So these are all rigid connections where the elements meet. Now, as you would expect, with the loads being perpendicular to the plane of the structure, not only are we going to have bending moment, but we're also going to get torsion. So both torsional and bending moment continuity exists at the node point of a grid. Can you think of an example that where we would use grids? Something like this. Wing. Yeah, sure. Airplane deck. A bridge. Right? So anything that's in plane and the loads are perpendicular, and it's made out of elements that make something that looks like a grid. Okay. So since we have some application in mind, we would like to develop the equations for a grid element. Develop equations for grid elements.
Coming back just 5 seconds.
Yes, of course. So development of grid element equations. As usual, we are going to look at a 2D element, simple. So we're looking at an element that extends between node 1 and node 2. And we are looking at local coordinates where the element is oriented along the x prime axis. So I'm using the prime for local. Perpendicular direction would be y prime, and the grid would be in the x z prime direction. The element has a length L. And the element extends from 1 to 2, so the local axis would be going in this direction, same as the x prime. So the first question we ask ourselves is how many degrees of freedom per node? Three. What are these? When this is loaded perpendicular, right, we are expecting to see deflections, right? So if I'm trying to describe the degrees of freedom, I would say that I will have a V prime, right? A V prime. And if this is node 1, I would call it V prime 1. What else? This is the first degree of freedom. Displacement. And the loads are perpendicular or transverse to the axis. So like the beams, we're going to get a rotation about the z-axis, right? So this rotation about the z-axis, I may describe it by phi 1 prime. Which is about which direction? When bending happens. Beam theory, right? The section is in the XY plane and it's bending about the Z, right? So I can say that this is F1 prime, and maybe I can put a Z. And the reason I'm doing that, when we did the beam element, we did not include the Z because it was, for granted, that was the only rotational degree of freedom, right? But here with a grid, my third degree of freedom as well is going to be another rotation due to twist. So it's going to be rotation about the axis of the element, okay? So I'm going to get, sure you can see the difference here. So I'm going to call this phi 1 prime x. So this is still at node 1. Of course, likewise, at node 2, we're going to have a v2 prime. I'm going to have a v2 z prime and this phi 2 x prime. So the first thing we can say here that we have 3 degrees of freedom per node, namely a v prime. I'm going to use an I because for any node, phi I z prime and phi I x prime. Since mostly the loads are perpendicular to the plane of the grid, the plane of the grid or the plane of the structure, we are going to ignore axial displacements. We're going to ignore axial displacement. Now, corresponding to these degrees of freedom, we are going to have 3 corresponding nodal forces. Namely, IY prime, MIZ prime, and MIX prime. So if I'm gonna show these on the elements, I'm gonna have here F1 Y prime. I'm gonna have here F2 Y prime. Corresponding to F1 Z prime, I'm going to have M1 Z prime, and corresponding to phi 1 X prime, I'm going to have M1 X prime. Here I'm going to get M2 Z prime. And by the way, this M2 Z is the bending moment, right? And corresponding to F2 prime X, I'm going to get an M2 X prime. This M2X prime is like the torque. Okay, so let's write down this FIY is a transverse force and MIZ, and let's keep the primes because these are with respect to the local axis. So MIZ prime is the bending moment and MIX prime is a torsional moment. Now, having spelled these out, do you see any correlation between a grid element and any of the elements that we developed equations for in the past? Which one? like a beam. So when we did the frame, we thought of a beam element and a bar element together, combined. So when I'm looking at a grid element, definitely we see a component coming from the beam element equations. But then the other component would be coming from an element that is purely in torsion. Okay, so like we did a bar element, we can derive a torsional bar element stiffness equations. So I would say here to develop the local equations of a grid element we need to include torsional effects in the basic beam element equations. Because the beam element equations account only for shear and bending moments. Okay, so we have a need to derive torsional bar element equations like we used the axial bar element stiffness equations. Stiffness equations, of course, and stiffness matrix. So I'm going to be looking at a bar element. And we are going to assume a circular cross section. So this has a length L, and this is the local axis X prime. At the first node or first face and the second face. Now here I'm going to have 1 degree of freedom per node. So here I'm going to get M1 X prime and a phi1 X prime. Also have M2 X prime and phi2 X prime. So we assume circular section. Now we're going to start by looking at the displacement equation. In this case, the displacement is rotational, right? So assume if we have 2 degrees of freedom, we want to have 2 parameters in the equations. So we're going to use a linear displacement function. So assume a linear angle of twist I'm going to put here the displacement variation along the local x prime axis. So I can write that phi prime is equal to a1 plus a2 x prime. Where we want to express A1 and A2 in terms of the known nodal displacements, in terms of the known phi 1 x prime and phi 2 x prime. So this is going to be very similar to the bar element we did in chapter 3, right? So I can get here phi prime equal to A1 would be phi 1 prime x plus, and A2 would be phi 2 x prime minus phi 1 x prime divided by L multiplied by x prime. So this is my displacement function along the length of the element. I can write this in matrix form. As a phi prime equals to n1, n2 multiplied by phi 1 x prime and phi 2 x prime. Where n1 is equal to one minus x prime over L, and n2 is equal to x prime over L. Of course, you will need to rearrange the displacement function given here in order to come up with the shape functions, but they're very similar to those of the bar elements. So I hope you can see that. So here we have shape functions. Next, we are going to look at relationships. So we're going to look at shear, strain, angle of twist, relationships, if I take a very small element, of this bar element, where this is x prime, y prime, and Z prime. And I'm looking here at the length dx prime. This is the center O. And if I'm looking at the xz plane, x prime z prime plane, so if you imagine this is before we have any displacement. After this goes in twist, when this goes in twist, the point A here, if this is point A, is going to move and become B, going through an angle of twist. This angle here would be d phi prime. And at the same time, this blue line will be curved like this. And this angle between the blue and the green will be gamma all the way through the lens. This is how we measure the shear strain. I'm going to call this gamma max. And the reason I call it gamma max, because I'm going all the way to the outside where I have the maximum the maximum angle. So I'm using the entire radius. So this blue line has a length r. And I'm going to call this point B. So the arc length AB is equal to gamma max multiplied by dx prime, and is also, if I look at the angle d phi prime and the radius r, is equal to r times d phi prime. If I want to solve for gamma max, we can say that gamma max then is equal to r d phi prime by dx prime. If instead of using the uppercase r, I pick any radial distance lowercase r, at any radial distance r, we can say that gamma, and it's no longer going to be gamma max, it's just going to be gamma, is equal to r d phi prime by dx prime. D phi prime by dx prime, I can express that as the change in angle over the length. So I can call it here phi 1 x prime or phi 2 x prime minus phi 1 x prime divided by L.
So you're holding one side fixed and then you put a torque on the other side.
Good observation.
Okay.
Okay. And that's why if you want to find the angle phi, you would subtract them from each other. So that's why when I did here, of course, this is a dx prime. But if I wanted to find d phi prime by dx prime over a length L, right? I did like when we did elongation. Elongation was, as you remember, U2 minus U1, right? That gives me the elongation. So by the same token, we did here phi 2 prime x minus phi 1 prime x.
So for the AB,
AB is this arc length here.
so for the R,
Arc,
from A to B.
correct. It's along the surface of this element. we also have a shear stress, shear strain, relationship. And of course, for linear elastic isotropic material, we have tau is equal to G gamma, like Hooke's law. So this is for linear elastic isotropic material. Where G is the shear modulus of the material. From mechanics of material, we have defined the torque that I'm going to call here mx prime. Now we understand that x is about the axis of the element. So you can think of this as the torque T, right? Mx prime is equal to tau J divided by R. Maybe you're more familiar by looking at tau equal to T divided by J times R, which is the same as what you see here. Now, in this equation, this is J, by the way. And J is the polar moment of inertia, right? J is the polar moment of inertia. If I substitute for tau, and knowing that tau is equal to G times gamma, and here is gamma, I can express mx prime as Gj divided by L multiplied by phi 2x prime minus phi 1x prime. So here we replaced tau that I was looking at here, knowing that tau is equal to G times gamma, and gamma is equal to R over L phi 2x prime minus phi 1x prime. Now I can use this to express m1x prime as Gj over L multiplied by phi 1x prime minus phi prime 2x. Please note that here I switched the order because originally we were looking at one side fixed, so really we're looking at the difference. And m2x prime is equal to Gj over L multiplied by phi prime 2x minus phi 1x prime. If I put this in matrix form, we can write it as m1x prime, m2x prime is equal to Gj over L. Remember EA over L. Here I got Gj over L multiplied by phi 1x prime, phi 2x prime, and here I have 1 minus 1 minus 1 and 1. This, of course, remind me was f prime is equal to k prime multiplied by d. Therefore, the stiffness matrix for the torsion bar is k prime equal to gj over L multiplied by 1 minus 1, so 1 minus 1 minus 1 and 1. Next, we are going to combine the torsional effects with the shear and bending effects and these are from the beam element that we derived earlier. To get the local stiffness equations of a grid element. So this K prime here is for a torsional bar element, right? And just that we have it all on the same page, I will write here K prime for a beam element. This is here a 2 by 2, right? For a beam element, this K prime was what? 4 by 4? And it was equal to EI over L cubed. And was a symmetric matrix. We had here 12. We had the 6L. We had minus 12. And we had 6L. Then we had the 4L squared. We had a minus 6L. We had 2L squared. And then we had here a 12. And we had here 4L squared. And we had here a minus 6L. And it was symmetric, right? So this is the stiffness matrix for a beam element. Now, if I want to write the equations for the grid element, we have F1 prime Y. We had, I'm going to write the torque here, M1X prime. Then I'm going to write M1Z prime, F2Y prime, M2X prime, and M2Z prime is equal to, and here I have my displacement degrees of freedom. So those are going to be V1 prime, V1X prime, V1Z prime, V2 prime, V2X prime, and V2Z prime. And we want to fill in all the elements for a 6x6 matrix. I want you to pay attention that if I go with the order here, if I go like 1, 2, 3, 4, 5, 6 for the degrees of freedom, and I label my stiffness matrices here, this will be 1, this will be 3, then I will have 4 and 6, and here will be 2 and 5. Can you all follow that? Okay. So now basically I'm gonna assemble my stiffness matrix by superimposing these two together. So we're gonna get 12 EI over L cubed. And then I'm going to have a 0. Then I'm going to get the 6 EI over L squared. Then I have minus 12 EI over L cubed. Then I will have a 0. And then I will have a 6 EI over L squared. So this is basically the first row from the beam element stiffness matrix. On the second row, this is going to be coming from that of the torsional bar element. Torsional bar element. So I'm going to get 2, 2, which is going to be GJ over L. Then I'm going to have 0, 0. And then I have a minus GJ over L. And then I have a 0. Next, I'll be looking at the third row, which is going to be coming from the second row of my beam element stiffness matrix, right? So I'm going to be getting here 4 EI over L. I will be getting minus 6 EI over L squared. I have here a 0, and I have here a 2 EI over L. Now, row 4 is coming from the third row of the beam element stiffness matrix. So for my diagonal element, I'm going to get here a 12 EI over L cubed. Here we'll get a 0, and we'll get a minus 6 EI over L squared. My fifth row is related to torsion, the twist. So I'll be getting 0 here, and on my diagonal, I'm going to be getting a plus GJ over L. And finally, I have here a 4 EI over L, which is coming from the fourth row of my beam element stiffness matrix. And of course, you see here we have a positive diagonal, and we do have symmetry. So we can say that this represents f prime equal to the k prime that we were looking for multiplied by d prime for a grid element. So this would be the local stiffness matrix K prime. Now, this would be fine if my x prime axis is oriented along the x-axis. But how about if I have an arbitrary orientation of a grid element? We need to do transformation, right? So we're gonna follow the same steps. Okay, so let's look here. If this is my x-axis global, this is my y global, and this is my z global. Now, if I have an element, again, my element, since the grid is going to be in the xz plane, so my element is going to continue to remain in the xz plane, but now it's going to be oriented at some angle. So here is my element. And now I can see my local x prime makes an angle theta with x. I'm gonna get a z prime that also makes an angle theta with z. So this is gonna be z prime, but y prime is gonna remain in the same direction as y, which makes things easier. So here we are looking at a grid element that is arbitrary oriented in the xz plane. Now, remember that if I want to come up with a transformation equation for the grid, or really a transformation matrix, if I'm trying to get a TG for the grid, we are working in 3D, right? And we are using 6 degrees of freedom, V and phi and phi, right? If I'm trying to express a vector, what would my transformation equation here look like? The first degree of freedom that we used was displacement along the y direction. Would this get affected? No. So if I'm trying to come up here with a 6 by 6, the first element would be 1. And then I'm going to have a bunch of zeros. 0, 0, 0, 0, 0. Likewise, on the 4th row, I'm going to have 0, 0, 0, 1, 0, 0. And the first column, 1, and then we have the zeros. And also on the 4th column, we're going to have the zeros except for this one. And now if we start looking at the going from X to X prime and from Z to Z prime, you will notice that we are going to use the cosine like we did before. So I'm going to have here a cosine sine theta. And on the third row, I'm going to have a minus sine cosine. And likewise, in the lower end of the matrix here, I'm going to get cosine sine minus sine cosine. And everywhere else, we're going to have zeros. So this Tj is the transformation matrix relating local to global degrees of freedom for a grid element. Where theta is positive, taking counterclockwise, yeah. Now, if you look at this theta here, the way I drew it, would you consider it positive or negative? Negative, right. So when I say really counterclockwise in 3D, this could be a little bit tricky, but if we're looking from the top, it's as if going in the clockwise and would be considered positive. So when I say positive, taken counter clockwise. So we have C equal to cosine theta and is equal to xj minus xy over L. And S is equal to sine theta is equal to zj minus zi over L. Like we did before, we can find the global stiffness matrix for a grid element that is arbitrary oriented in the xz plane. So this K global would be equal to TG multiplied by K prime for the grid element multiplied by TG, and this one here is transpose. So I'm taking the transformation matrix for a grid transpose multiplied by the lowercase k, the element stiffness matrix of the grid with respect to the local axis multiplied by the transformation matrix for the grid. And this can get interesting but I would just do it numerically for each element as we go.
What if you have two different angles? If elements are shifted by two different angles?
Remember, because we are maintaining the grid in the XZ plane, so it's going to be corresponding, right? Because we're maintaining Y oriented along, or Y prime always going to be oriented along the Y direction for a grid. Yeah. But what you're saying here would be interesting if we do it for a frame element in space, right? So we did it for a frame element in plane, but this would be true because a frame element, once you start going in space, you're going to have three different angles.
Is that grid, is that located, is the frame of that grid on that angle? Would all the forces be perpendicular to, it would be at an angle as well, right?
All the forces are still perpendicular to the element and perpendicular to the plane of the structure, which means the forces are going to be applied only in the Y direction.
Because the structure is in the XZ.
Correct.
Okay.
So we've been keeping that since we started today talking about the grid. We started with the structure in the XZ,
I see.
right? So you can see, for example, these elements are making an angle 90 degrees with the X.
Gotcha. It's the same thing. They're also XZ. Yeah.
Okay. Now, of course, I have to mention that grid elements do not have to be circular members. So because of that, we are going to have to find like polar moment of inertias for beam sections like a channel. So this is the J you're going to be using. And for an angle, here is the J, and a Z section or a wide flange beam. These are all available in your textbook to use the corresponding polar moments of inertia. I would ask you to please go over examples 5.5 and 5.6 in your textbook. The process is very straightforward, like we did frames, but I think it would be nice to go over it before you attempt the one homework problems on grid. Okay, this will conclude